Welcome back. In this lesson, we're going to look at the seismic waves when an earthquake happens. So if you have two huge masses of rock that are rubbing against each other or past each other, and they form a vibration, an intense vibration, they are going to send out waves through the material inside the earth and on the surface of the earth. So there are various waves that we've looked at in the past lessons, and we'll see that the speed of those waves can be picked up at seismic stations all around the world, and predictions made out of where that earthquake was. And unexpectedly, as we are studying earthquakes, we also can, as we study these vibrations that occur in earthquakes, make certain predictions about what the internal structure of the earth is. So though no one has ever dug down into the deep core of the earth, they can make predictions as to temperature and materials and whether something is solid or liquid. So let's look at some examples. If you drop a pan of Jell-O, it'll wiggle. And that's exactly what happens when rocks bang off of each other in an earthquake. Everything in the earth wiggles, and it wiggles based upon what it's made out of. So the more gelatinous it is, the more it's going to wiggle like Jell-O. The more hard it is, the more it's going to wiggle like rocks. And since everything wiggles in a different way, you can learn a lot about the inside of the earth that we'll never be able to go to just by sending vibrations through the earth. So when you are measuring vibrations of the rocks as they resound off of each other during an earthquake, those things can teach you a lot about the inside of the earth. And if you send vibrations down into the earth yourself, so you make vibrations, you make waves by explosions and different things like that you on purpose send out so that you can then measure the effects of them. If you remember, there were three types of waves. You had P waves, which are primary waves. Those waves are going straight forward. That's a concussion wave, very much like sound, and it goes through solids. And it will reach a far distance fastest. It's the fastest traveling wave. So if you have a place that's measuring vibrations, some kind of a seismic center that's measuring the Earth's vibrations, then any time that you would have an earthquake anywhere in the world, that place would receive the P waves first. The second waves, or the S waves, are secondary. They are going to get there second. And then the third type of waves only go on the surface of the Earth, and it may or may not reach the seismic center, but if it does, usually that's going to be last. So because certain things can flow in solids and not liquids, certain things can flow faster in colder than hotter or hotter than colder. So all of these waves travel in different ways based upon what it's traveling through. You can make predictions, or you can make guesses about what is under the ground, whether or not it's solid or liquid, whether there's different layers under the ground, or whether it's one big solid chocolate bunny. Okay, so the first thing is that these seismic waves are these waves that are bouncing around after two rocks have an elastic quality. So if you pull one rock back and then let it snap and it resounds, boing, 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 what you're picking up in the earth and on the earth is the vibrations that those rocks make as they pull away from each other, and then there's an elastic kind of a bouncing back quality to one side and another side that's making these movements. You pick these up with a seismometer. And a seismometer is very sensitive. Usually it's something very heavy. So what's happening is that it's either mounted to the floor or mounted to some piece of huge stone or something like that that's not likely to move. And then in order for this seismometer to pick up a reading, the entire floor has to be shaking. Okay, so that's one way to do it. There's also a big weight there that is connected to the pin in such a way that that weight does not want to move. It has inertia, and because it has inertia, it's very heavy, it wants to stay still. And so it really does take a real vibration in order to get that weight to move and the pin to make a mark because of its movement. So these are very sensitive tools, normally on some kind of a spring. And then the paper that's left over after it makes a move, so it's usually an electric drum that's moving and the paper is going around it. And as the paper is being marked on, that paper is now called a seismogram. So something that is marked. Now, a lot of times that's done computer recording rather than paper reporting, but I believe there still are paper seismograms. So you can see that in this seismogram, the amplitude is how big of a shake it was, and how long it shook was the number of times, the amount of time it took for the primary waves to reach the recording place and the secondary waves. Normally it's those two that you're measuring in some kind of a seismic recording place. Right, so the P waves come in first. That's the small ones. The secondary waves are the ones that are shaking back and forth. Remember, the primary waves are kind of into each other. Okay, so that's like an in and out. One rock shoving into the rock in front of it. And so it's moving forward very fast. That's why it gets there fast. The secondary waves are kind of going up, down, side to side. And so you get more of a violent pin shake when it finally does reach the recording place. So the time it took between the primary waves starting and the secondary waves to starting is recorded, and then the amplitude of how big of a shake is recorded. Those are the two major things that are recorded in a seismogram. Now the curve is essentially how far is, in an amount of time, how far does a primary wave go, how far does a secondary wave go, how far does a surface wave go in a certain amount of time. You're going to see that the P waves are the fastest, the S waves are the second fastest, the surface waves always catch up later. And so you can make predictions of how far away at least the surface of the Earth was. Now the movement may have occurred very far underground, but at least where on the surface of the Earth was that shake? Where was the originating of that shake? Simply by how fast that these come in and what's the time in between one and the next. Because they travel at a certain speed, you can measure that speed, so then you can make predictions of just mathematical solutions of how far something is away from you by how long it took the P waves and S waves to get to you. Now, that doesn't tell you exactly where it is. It just tells you how far it was from the station. So if you were just to get one seismogram in one location, I wouldn't know where it happened. I would only know that it was exactly 511 miles from me. So wherever that was, 511 miles, there's a circle that's exactly 511 miles from, and I'm making up that amount. I simply take that math and figure out the difference between the time the P wave started shaking and the S wave started shaking, and then I can, from that speed, find out how far away it is. Now, if you have more than one station, and each of them is making a curve, remember, a circle around of how far something is. So let's say a different station, that same shake was 1,300 miles away. So I'm making a circle around my station 1,300 miles around, and that first station, it was 511 miles, so it's going to make a circle 511 miles. And then as soon as you get three stations, three circles intersect only at one point. Two circles could intersect at 2 points. So if you had only two stations, you could overlap a circle at two different points. But if you had three circles, the only way that they could overlap would be at 1 point. and that is where you would note that the epicenter was. Okay, so the epicenter is always going to be at the overlap of 3 seismic stations when they figured out how far away that the shake was from their station. That overlap was going to be the epicenter. And remember, the epicenter is going to be on the top of the ground, and the shake could have been deep underground, but the epicenter is on top. Okay. Now, the P waves can go through the ground. An S wave can go through the ground, but a surface wave is only at the surface. And so that's why that it's going to move much slower. It's much farther to go around the long way than it is to go through the Earth from from its location of shake to the seismograph station. Okay. Now, just because we've figured out these shakes and essentially the math that goes along with it, we can make some predictions just about the inside of the Earth. There are clues to the interior structure of the Earth simply by how that these tremors are recorded. Okay, so we're going to see that an S wave doesn't travel through liquid. So anywhere where S waves stop and don't go all the way to the other side, you can make a guess that there's something liquid inside the Earth at that place. Okay, so if you start measuring different shaking, and you can pick it up at one seismic station but not another, it means that the S wave is traveling through solid to get to the first seismic station, but since it never reaches the second, it must be headed into liquid on the internal part of the Earth. So you can make guesses that there are inner and outer layers inside the Earth, some of them liquid, some of them solid. So as of right now, you're going to have a solid inner core as the model that we have of the inside of the Earth, that you have a solid iron core or some kind of a nickel iron composite, because these sound shakes will travel through different materials at different rates. And so as you're finding out how fast, if you knew exactly where something was and you knew how fast it's supposed to travel through this material, and it travels that fast, then you can guess that it's that material. So you can, over many, many, many experiments, kind of figure out, well, what is the primary component of the rocks under the ground at this depth or at this depth or at this depth, and you can make guess after guess after guess and clean it up with more experimentation. But as of right now, you're going to say that you've got different temperatures, because temperatures will affect these with vibrations. Materials will affect these vibrations, and whether something is a solid and a liquid will. So knowing those 3 things, that these vibrations will travel differently depending upon solid and liquid, and whether it is or some kind of a semi-solid, and different in terms of temperatures, and difference in terms of materials, you can make certain guesses about what's on the inside of the Earth, even though no one has ever been there. So, as of right now, you can see that P waves and S waves don't bounce back from an epicenter of an earthquake in a certain range. In this picture, it's gray, that there are no S waves and no P waves. So that it's called a shadow zone. And since it's a shadow zone, that means that it must be trying to pass through liquid. But if you can get P waves to travel through solid, and so you can get right across from the core, you can get no S waves, but you can get P waves. That means that there must be some region that's liquid and some region that's solid. And so the best that we can figure out right now is that you have a solid iron core and then a liquid outer core. And then everything else is solid, semi-solid, plasticky kind of sloshy solid. Okay, the remaining of the mantle and upper crust is that. So this is our guesses based upon earthquakes. So knowing something about one thing can lead you to knowing something about another thing.